Okay, so this is going to be the second part of our lecture where we're going to talk about naming of our compounds. Now, the reason why I wanted to do this as a separate one is that it's actually a little bit more involved of a process and it takes a lot of practice. So you want to make sure that you're working your way through it. And so the first part about naming the compound is we need to know how the compound is bonded, how it's connected. Because once we know the types of bonds that it forms, then we know what style of naming we should follow. So the first question is that there's three types of bonding. There's what we call an ionic bond, a covalent bond, and then a metallic bond. Now, we're not going to worry about metallic bonds yet. We're going to come back to that. But we are going to worry about ionic bonds and covalent bonds. Those are our first ones. So chemical bonds happen because those atoms are more stable together than they are apart. So there's a benefit that they gain from there. There's a lowering in what we call potential energy. Now, we're going to get more into our bonding later on in the course. Right now, I just want to give you a brief overview so you can get introduced to it. Now, the important part to remember is that our ionic bonds, they happen between metals and nonmetals. So we already looked at the periodic table. We can tell the difference between a metal and a nonmetal. And so what's happening in an ionic bond is that those electrons that form that bond, they're being transferred. And that's because our metals like to give away electrons, our nonmetals like to take on electrons. On the other side, we have what we call a covalent bond. And the covalent bond happens between two nonmetals. Now, in the covalent bond, those electrons are shared. We're sharing those electrons between each other. And that's because neither of those nonmetals is strong enough to take away the electrons from the other one. And metallic bonds happen between two metals. So the first thing we're going to look at is ionic compounds. Now, they form generally between metals and nonmetals. And this is because we're transferring our electrons all the way across. Now, they form these giant crystals like this. So instead of forming these discrete molecules, they're really held together by these attractions between them. So when we're looking at ionic compounds, we want to think of them as being this connection between our anions, negatively charged ions, and our cations, positively charged. And they don't form molecules, they instead form these ionic crystals like you see here with this green and this purple. That way, each of those anions is attracted to a cation, but it could be spread out between several cations, several anions. They're not directly only tied to one other one. Now, this is different for covalent compounds. Covalent compounds make what we call molecules or molecular solids. So these are held together by these covalent bonds where the atoms are actually sharing electrons between each other. And so this sharing ends up with them having a directed bond or connection. That means that those atoms are connected to just each other. They're not connected in the same way that an ionic lattice is, so they're not spread all the way out. So when we think about this, when we're trying to classify them, ionic compounds involve ions. So we should be looking for anions and cations, or metals and nonmetals, whereas our molecular compounds are our covalent ones. This is where they're sharing electrons. They're not just transferring electrons. So we want to make sure we can identify which one is either a molecule or which one is ionic. So take a moment, go through that. The big part to look at is whether you're a molecule, whether you're a metal or a non-metal as you compare. So NaCl is a metal, sodium, and a non-metal chlorine, so that should be ionic. Whereas H2O, hydrogen is a non-metal, and oxygen is also a non-metal, so that's going to be covalent. And so that's how we can get an ionic one for NaCl, and we can get a molecular one for our H2O. So take a moment, continue on through your next ones, so that way you guys can practice. And this is our answer right here. It's all about identifying them as either being positive or as either being metals or non-metals, and then using that to separate our ionic versus our covalent. Now, the reason why this is important is ionic molecules follow their own pathway with how we name them. Covalent ones follow a different pathway. Now, in the Canvas page, I've linked to you a worksheet that kind of helps breaks this down. So it gives you a flow chart, so you can kind of use that as you work through and you start to do your naming. Now, you won't be able to use that on your exams and your quizzes, but it is a good way to start out when you're first practicing naming those compounds. Now, what I would say about naming compounds is it is a tricky thing to do in the beginning But by the end of this class, it should be very comfortable. Now, the secret to that is practice, practice, practice. Naming compounds is kind of like learning a foreign language. If you don't practice it a lot, it's harder for it to sink in. And so you want to make sure that you've done hundreds of these by the end of this course. Now, what I normally recommend is, if you think about it, if you just sit down and do 10 of them a day, in 2 weeks, you'll have 140 of those done. Right? And you should feel much more confident with your naming of your compounds. Now, for ionic compounds, it's pretty simple. We start off with the name of the metal. So that goes first. So in something like NaCl, we start off with the Na, which is our sodium. And then from there, we go to name our anion, the nonmetal. Now, in this case, it was chlorine. And so we're going to change the ending of chlorine to chloride. And the reason why we do that is to show that now it's part of that bond. If we just said sodium chlorine, that doesn't imply that they're together. But if we call it sodium chloride, then we know that those are connected. And so that's how we first start going through our naming process. So we have sodium chloride, in this case K2S, this is our metal, this is our non-metal. So we get potassium sulfide, right? Magnesium oxide, calcium iodide, aluminum sulfide, right? And that's kind of how it looks like as we go down. Now, sulfur, when we wanted to change that to sulfide, we just took out this U and this R. Oxygen, when we wanted to change that to oxide, we took out the YGEN, right? So nitrogen becomes nitride. Okay, so that's the basics of it, but that's not the only part. So we're going to practice these simple ones first. Go ahead and do these 4. So this should be calcium oxide. Spelled that wrong. Potassium bromide. Aluminum sulfide. Magnesium chloride. But so far, we've been getting lucky. And the reason we've been getting lucky is that with our metals, what you might not have noticed is the only metals I've given you so far have been our main group elements. Now, our main group elements, we know what ion charge they should be making based on where they're positioned on the periodic table, which we talked about in the last video. Right? So when we looked at the periodic table for our main group elements, we could get an idea about what charges they had, because this first column, our alkali metals, is all +1. Our alkali earth is generally all +2. Our aluminum metals are +3. Right? But for these other ones, our transition metals and what we call our post-transition metals here, basically the metals coming after the transition metal grouping, they follow a different set because they can have more than one charge. And so we have to indicate that. We have to provide that. And so we're going to give them in their Roman numeral. So this complicates our naming just a little bit, because now when we name them, because these transition metals can have more than one charge, we have to indicate which one we're talking about. Are we talking about iron 2+, or are we talking about iron 3+? And so we have to indicate that. And so this is where that extra part of the naming of ionic compounds comes in, where we have to give Roman numerals. So this is an example of that. So chromium 2+ becomes chromium with a 2 written after it. Chromium 3+ will be chromium, but with a 3 written after it. So this number that comes afterwards, it isn't telling you how many atoms you have inside of that. It's telling you the charge of that atom. So you'll see this with anything that has a variable charge, or what we mean by that is our transition metals and our post-transition metals. Now, there are a few of the transition metals that only have one charge. Things like silver is almost always found as a +1. And zinc is normally found as a +2. But I won't mark you off if you include the charges. I won't mark you off if you don't include the charges in those cases. However, for ones where they have more than one charge, so things like gold or iron or lead, if you don't include those Roman numerals, then you won't be able to get all of those points. So you want to make sure that you do understand how that works. So we're going to do an example. We're going to look at CrO. So CrO is made up of chromium and oxygen. So chromium, we would name that first, chromium. We would then indicate its charge. In this case, it's a 2+, so chromium 2. And then we would call that oxygen and change it to oxide. So that's how we get chromium 2 oxide. This is another one. This is iron chloride, FeCl2. And so we want to go through those steps. So the first one is looking at that compound. We should identify our charges. So the iron ion and the 2 chlorine ions must be equal to each other. So the iron ion is going to become a +2. Now you can see this because one of those iron ions balanced out 2 of those chlorine ions, and each chlorine was a -1. So we know that iron is of 2+. So we want to go through and want to name that, showing that it's the 2+ state, iron 2. We then write the anion, in this case chloride. And so when we put all those together, we get iron 2 chloride. Another one would be one that looks like this. So this is our chromium and the oxygen. So we determine the charges first. Chromium becomes a 3+ because there's 3 of those oxygen, and each oxygen is a -2. We have 2 of those chromiums trying to balance out those -6 charges of the oxygens. So that means our 2 chromiums, each one must be a +3. So that's how we get the chromium 3. And then we add in the oxide, the name of the oxygen. So you practice these, and let's see if we can come up with the correct ones. So Fe2S3, our iron in this case is going to be 3+. So we should have iron 3, and then we have sulfur, which is sulfide. And we know that the iron needs a Roman numeral charge because it's a transition metal. Copper, looking at it, copper is still a transition metal, so we know it's going to need a Roman numerals. Now, 1 copper is equal to 1 oxygen. That oxygen is a -2 charge, so our copper must be a +2 as well. So copper 2 oxide. You want to feel comfortable going backwards and forwards with this, so you should go from the formulas to the name or from the names to the formula. So in this case, when you're writing the formula, you just go ahead and identify the cation. So in this case, that's going to be potassium and our sulfide. We can then balance the charges. So we need 2 of those potassiums for every 1 sulfide. And we can write those together, K2S. Same thing if we have our iron 3 chloride. We identify the cation, so iron 3+. The chlorine is a -1. We balance those charges, so we need 3 of those chlorines for every 1 iron. And so our chemical formula should be that FeCl3. You can do the same thing down here. In this case, we have our copper 1 nitride. And so we want to think about our charges. In this case, copper 1, that's Cu1+. Nitride is N3-. So we need 3 coppers to every 1 nitrogen. Lead 4 oxide, well, that's Pb4+. Our oxygens all are 2-. And so we should have 2 of those oxygens for every 1 lead. And so we might choose 1, we might choose 3. What we want to think about is we want the smallest ratio of them. So we want to go with 1. Okay, and so you want to make sure that you're practicing those, that you feel comfortable with them. Now, polyatomic ions, they're just a group of atoms that have that same overall ionic charge. What's different about them is that they get their own name. So some of our common polyatomic ions are here, but I've also including a list for you guys inside our equation sheet. So if you pull up our equation sheet, bringing that on over. Our equation sheet has got a periodic table on one side, but down here it also has our polyatomic ions list. So any of these ions that show up down here, they're showing up as a grouping, and that entire grouping has that charge. So +1, 1 minus, 2 minus, as you're going through that. Now they get special names for them. So they might end in something called 8, or they might end in something called ite, right? As you work your way through. As you become more familiar with them, it should feel more comfortable. Right? Your book does have a chart of them as well. And so that ending, we no longer want to change. We don't want to change it because it matters, right? Outside of the hydroxide, all of the other ones end in something different. So they end in ammonium, 8, ite, and that 8 or ite becomes important in telling us information. So when we have a polyatomic ion, and we're using that to name with, things like this are ammonium perchlorate, what we're going to do is we're going to leave them together. We're not going to change their names or their prefixes. We're just going to put that name in. So this is going to be an example. We have sodium here, and we have NO3 with a -1 charge. So it should be 1 minus. So when we name that, we're going to name our metal first sodium. But we don't need to change anything about that NO3 minus. We just called it what it is, nitrate, because it's that collection of them. If you have more than one, then we need to put them in parentheses to show that we have 2 of those nitrates. But the naming goes the same. We still have magnesium. And since that's a main group element, we don't have to do any Roman numerals. And then we just call it nitrate. So we don't change the ending anymore. We don't change it to nitride. We leave it as nitrate. So polyatomic ions, they stay the same. Now, if we did have a Roman numeral 1, so let's say we have Fe3, and let's do it with our PO42. Fe3, well, this one, we know that a phosphate is a -3 charge, and there's 2 of them, so that's -6. We know our iron, there's 3 of them, so iron must be +2, so that becomes iron 2. And then PO4 is phosphate. And we got all of that from our list here, right? Phosphate here has a 3- charge. And so that's what you're doing with your polyatomic ions. So you're going to get a flow chart that kind of looks like this as you're practicing through it. And so you can use that to help you identify, right? If you have a metal, then you're going to be in the ionic compound. If you only have nonmetals, then you're going to go through a different naming system because those will be all identified as covalent. Now, your lab manual also has some of this inside of it. It's called Study Assignment A, and I've linked that below as well. Now, Study Assignment A, if you need some more support for this, it has really detailed instructions in how you go through and name your molecules and your compounds. And so it's a good one to use as you're going through. I would definitely recommend practicing through all of these because it is very helpful for you guys. Okay? And so you can keep going with that. So this is our covalent ones. Or sorry, this is our ionic flowchart. And that's what we're going to start with. Now, inside that flowchart that I've connected you guys to, it also tells you what to do if it's only covalent compounds. So that's what's this one's, so that's what's going on here, is if it's doesn't have any metals, then it's going to be considered what we call a covalent compound. We're going to look, is its first element hydrogen? If it is, then it's going to become something that we call an acid. Now, we'll get more into why they're called an acid, but basically, if it starts with an H, it's going to be an acid. And so we're going to go through this naming rule. So if it's just the H with one other element, then we call it hydro. And we look at the other element that's not the H. So let's say that we had something like HCl, that would become chlorine. We change that chlorine to chloric, and then we name it acid. And so that's how we get hydrochloric acid. If instead of chlorine, it might have been an F, then we would call it hydro, and then we change that fluorine to fluoric, so hydrofluoric, and then we end it in acid. So acids are always pretty easy to identify because they have the name acid at the end. And they also have hydrogens primarily, right? And so that's what we're looking for. And so that's how we can tell. Now, if it doesn't have them, if it's only non-metals, then we look. If they're the same element, then we just name the element. So nitrogen is N2, iodine is I2. And those are all those ones that show up as diatomic molecules. So that's the 7 that we know about. If it's not, then what we're going to do is we're going to use these different prefixes to identify them. And so we're going to find those prefixes using mono, di, tri. So the prefixes I've listed on the back of this flowchart that I found. And so you can use those to practice. So what I would recommend is start with this flowchart, try to practice naming these as you're working your way through. And if you have any questions, make sure that you guys ask. Naming compounds is a tricky part. So you want to make sure that you practice. We won't have them on the quiz next week, but they will be on the quiz after that, and you need them by exam number 1. So you want to make sure that you are practicing and you are asking questions. We will go more in depth with covalent compounds and ionic compounds, covalent compounds and acidic compounds next week. But you already have some of them on your homework because I want you guys to start practicing. It's really important that you guys practice them. It takes a while to master, and it's all about repetition. Okay, good luck.